You can tell me either way, just raise your hand, or please interrupt with questions. So what I'm going to introduce you guys today is parallel visualization with Python, and mainly concentrating about what we're going to go over tomorrow in the workshop. So I'm going to go through what is visualization. That's an easy one, sort of. Why should we bother with doing parallel visualization, and why Python in particular. The last one should also be easy. We're all at EuroPython, of course. Python, yes. And then I'll go over kind of, with pretty pictures, what we're going to be doing tomorrow afternoon. So first of all, why visualize information at all? So if you have a set of numbers, maybe in a spreadsheet, in a binary file, by visualizing it, you can gain some insight into patterns in your data, more easily communicate to a scientific colleague, a coworker, or a customer what does this data actually mean. You can easily compare your results either to your expectations in debugging, or to what someone else, a coworker or a colleague, got out of a particular computation, and you can gain some appreciation. So here are two beautiful visualizations. One's of shipping patterns around the world, and the other is a magnetic field. And you can see that not only do these help us gain insight and communicate kind of what the base numbers of the data are up to, they're also very beautiful. So now, why parallel? So desktop machines these days have many cores, 2, 4, 6, 12, hopefully more and more. And by fully using these cores, you can gain speed up if you're doing visualization. Moreover, datasets nowadays are getting bigger and bigger, and people are tackling the problem of visualizing and analyzing datasets that are too big to fit in memory on your local machine. So two examples here are n-grams, which are strings of words, where n is the number of words in the string, and Google releases a freely available data set that's used by a lot of people in natural language processing, denoting the frequency of a given n-gram in, say, the English language. So how often does the word dog or dogs suck, that string, occur in English? I'm a cat lover. Or that data set is 2.2 terabytes of data, so that's not going to fit in my MacBook's RAM, maybe next year. And Wikipedia traffic stats are 150 gigabytes. So if we really want to be able to interact with our data, and like I said, that helps us to discover new patterns in our data, and then we can act on those patterns to either debug our code, make our code run faster, investigate a certain phenomenon in more detail. Then we have to fully utilize our computational resources. So use those many cores and fully analyze the full data set by using many machines. So now, why ParaView? ParaView is, first of all, open source. It's written in C++ under a VHD license. It's very well maintained. It has a large development community behind it. And basically, it's a set of wrappers over the visualization toolkit, which handles a lot of the nitty-gritty elements of visualization for you with a Qt GUI. We just learned a little bit about PyQt in the last talk. So Qt graphical user interface and some parallel rendering libraries on top of that. And everything is neatly wrapped in several different languages. My favorite, of course, being Python. And here's kind of ParaView's model of computation. So you can have a serial reader, in which case the first part of this diagram would just be one big block. But if you have a parallel reader, then each process reads just a portion of the data that it's responsible for. And then you can optionally redistribute the data with a data distribution filter to have, for example, more spatial locality. Or if you have a serial reader, you might read in all the data on process 0 and then want to distribute the data among all your different processes. So in ParaView, there's just one function that you call, and it takes care of that for you as best it can. And then, if you want to do some analysis or visualization, There's the full VTK pipeline where you can have, in Paraview's language, filters. These are basically analysis or visualization functions. And then finally, you have the ICE-T parallel rendering library. And basically, each process renders whatever data it happens to have locally, and then ICE-T takes care of compositing all those different images. Here we have 3 images into a final image that you actually see on screen or output from your script. So now why Python? I mentioned that there's a great Qt GUI for Paraview that you can interact with by making some mouse clicks and quickly get up and running with visualization. And you can moreover extend Paraview in C++ by extending some of their filters or readers by implementing a single method. It's not too difficult, and you implement some XML to let the graphical user interface know about your extensions. But with Python, we can easily automate a lot of our mouse clicks, so you get tired of that as a researcher, clicking around with the mouse very quickly. And moreover, you can embed all of your visualization and part of your analysis into your existing Python code. So if you have a Python code to generate data, you can immediately visualize it kind of in line. So here's an example, and I will go through this in more detail at the tutorial. So what progress are we going to make in this tutorial? So we're going to go over creating simple visualizations in serial and in parallel. Here's an example where I'm actually connected to a parallel server that I started with this command, MPI run number of processors 2. This was on my local machine, and I have 2 cores. And then the PV server command, and connected to that server. Then I created a sphere. I showed the sphere, which basically tells Paraview I've made some changes to the data pipeline, recognized those changes, and then I render the sphere on screen. And if I save the image then, it would just be a gray image, but then I color by the process ID, and here I'm connected to a server with running on 2 processes, so when I show that and color by the process ID, you can see here I have these 2 colors of the sphere, red and blue, and this is way more fun to double check when we're running on like a 1,000-core machine that you're actually connected to the server, and you really can't believe it the first time you do it. So seeing it visually this is one of those things where it's good to debug your server just to be able to visualize, okay, here is the data, where exactly is it living, and if you're expecting processors to handle data that's very close to each other, being on the same process, you can visually immediately see if your data distribution works or not. So we'll be able to do this kind of right out of the box there. And then we'll go over reading in data from a comma-separated value ASCII file. That's going to be a serial reader, but we can then use the data distribution filter to, if we're running on multiple processors, if you have multiple cores, or I have a server set up, we'll be able to see which process your data lives on, as well as binary files. This is an example of a little bit of a random number generator, and I colored by the size of the random number, and also scaled the sphere by the size of the random number. And here's some of the Python code. I won't go into this in detail right now, but we'll cover this all in a few hours tomorrow, and also making modifications of this to suit your needs. We'll play with some data from the web. This is some stellar cluster data that's freely available that we can visualize and manipulate. We'll use filters to do analysis. So here's that previous random number generator where I've just thresholded by random numbers that lie between 0.75 and 1. So you see that now I only have big blue spheres instead of small reddish spheres. And writing their own custom readers, writers, and data filters, all in native Python. So finally, we'll go over what's possible, and I'm open to brainstorm with guys if you have a big or small data set that you're interested in visualizing how exactly peer review might suit your needs. And it definitely is possible to visualize and manipulate terabytes of data in one go in real time, given the computational resources. I've looked at billions of particles and done analysis tasks in real time via peer review. And so I hope that you guys manage to make it tomorrow, and everything should be very accessible for anyone from beginning Python, beginning visualizing, beginning scientific analysis to, if you have a huge data set, being able to write your own custom extension and get visualizing it right away. So if you manage, please download and run a peer review binary. There are binary builds for Windows, Mac OS X, and Linux, of course. I will also have these on USB keys and running on a local server at the tutorial if you don't manage to do this. And if you have problems with this, please ping me. So thank you very much.
Questions? Don't be shy.
Do you have any pointers to like freely available data sets that are actually interesting to visualize?
Yeah, I have, well, it depends on what field you find interesting, of course. But there is a lot of data freely available on Amazon S3, for example, their server cluster, and they even index it. Amazon has a freely searchable list of freely available data on S3, and there are, I think, 1,000 different huge data sets. So both the engrams and the Wikipedia traffic examples in my talk were taken from just searching that list of what's interesting out there. So if you have a huge data set you want to visualize, you probably need a huge cluster, and unless you're at a university, you might want to run on Amazon, for example. So having the data already at Amazon saves you the trouble of transferring 2 terabytes of data to your server, which is always annoying. Any other questions?
Is the library fit for visualizing the finite element analysis data or computational fluid dynamics results?
Yes, absolutely. It actually natively handles a lot of commonly used formats in both those fields, and you can definitely write your own custom extensions. There are lots of the primitive data sets in BTK or peer review that handle, say, moving meshes, etc. So if you're very lucky, you can even pick your favorite data set and use it out of the box. If you're slightly less lucky, you might have to write some lines of Python or C++ to handle that, but it's very suitable for both those fields.
And how does it work with large graph layouts?
I haven't personally done that. There are a lot of customized extensions plugins. So I maintain one plugin that deals with a few data sets and analysis tasks that are very common in astrophysics. And I do know that there is a computer science plugin called InfoViz that handles a lot of the graph visualization topics of interest, but I haven't played around with it myself. So I can look into that a bit if you're planning to come tomorrow, but my intuition is that it is suitable for that, but I just haven't played around with that as much.
I knew that there weren't many questions.
Is this platform dependent or platform independent? You run in the Macintosh or?
It's platform independent. It uses CMake as a build system, so even the build process is, I built it personally. I've never built it on a Windows machine, but I supervise a student who uses Windows, and he had no problem developing and running on Windows. And I built on anything from my local Mac to a Linux-based supercomputer, and really sometimes, especially when you're setting things up on a supercomputer, things can get a little hairy in compilation, but definitely for your local machine, it's very easy to compile.
I have a question. So, if there's any company that is interested in using it for the automation of commercial applications, what are the licenses?
So it's under a BSD license, and I believe that means that you can incorporate it into your commercial products and you don't have to release the entire source as it's the GPL. So I am aware of several commercial products that use Fairview.
Okay. Any question? Okay. So, thank you.